speed, and velocity. In this session, we have three goals. We're going to discuss speed and velocity and see how they're different. We'll learn how to calculate average values of speed and velocity. And we'll also learn how to find instantaneous values, which we often find from a graph. Speed is, velocity is, what do you think? Well, speed is a scalar quantity representing how fast an object is traveling, while velocity is a vector that combines the speed with the direction of motion. We can also define velocity as the time rate of change of position. The speed at any instant is the magnitude of the velocity at that instant. Here's an example of how you say speed. For instance, 50 kilometers per hour. For that to be a velocity, you'd have to combine that with the direction, 50 kilometers per hour north, for instance. Sometimes we want to know the average values, averaged over time. Average speed is something over the total time. Average velocity is something different over the total time. Or V average, V with a bar on top, is something over delta t, expressed as an equation. Well, the average speed turns out to be the total distance divided by the total time, while the average velocity is the net displacement over the total time. V is delta x over delta t. So let's do an example. Let's say you move 10 meters to your right, and then 4 meters to the left, and then 8 meters back to the right. You did that in a total time of 10 seconds. So, what's your average speed? Well, you don't have to worry about the direction of these displacements when you calculate the average speed. You just add up the distances. 10 plus 4 plus 8. 22 meters. Divide by the total time, 10 seconds. You get an average speed of 2.2 meters per second. Let's compare that to the average velocity calculation. Here we do have to take into account the directions. So it's all one-dimensional, so we'll use positive to indicate motion to the right, negative to indicate motion to the left. Then we add up the displacements, plus 10, minus 4, plus 8. That gets us a net of plus 14 meters. That means 14 meters to the right. Again, divide by the total time. The average velocity turns out to be plus 1.4 meters per second. Note that the average speed will only be equal to the magnitude of the average velocity when there are no changes in direction. Sometimes we're interested in instantaneous speed or instantaneous velocity, the values at a particular instant. So when driving, what in your car would you use to find your instantaneous speed? Well, of course, that would be your speedometer. If you drive from Boston to New York City, what in your car would you use to find your average speed for the trip? Well, you need to combine two things, right? You have to know the distance, that is given by your odometer, and you have to know the time. So there's probably a clock in your car that you can use to figure out how long it took you. If, while you're driving on the Mass Pike, the state trooper gets you on the radar gun, is the trooper interested in your average speed or your instantaneous speed? And of course, they're interested in what is your speed at that instant, and what they get on their radar gun should agree with what is measured on your speedometer. So you should know whether you're speeding or not. Let's talk about instantaneous values. So we have our average velocity equation. The instantaneous velocity equation is the same equation, delta x over delta t, but in the limit as delta t goes to 0. So for a tiny time increment, how far do you travel? Divide that little distance by that little time. That's your instantaneous velocity. And the instantaneous speed is the magnitude of the instantaneous velocity. Well, that's a great definition, but sometimes it's easier to get the instantaneous velocity from a graph. So, we'll make use of graphs. Complete these sentences. The instantaneous velocity is the blank at a particular instant on a position versus time graph. And of course, that is the slope. The displacement, on the other hand, is the blank, it's a larger blank, notice, for a particular time interval on a velocity versus time graph. And that turns out to be the area under the curve. So let's see how these work. So we'll take a position versus time graph and look at the slope. So we'll do two different ones. first we'll do constant velocity. So here we have a truck traveling at a constant velocity. We're plotting the position as a function of time. What happens here is that it goes at constant velocity, so the position versus time graph has a constant slope. And the value of the slope is, in fact, the value of the velocity. Now we'll do a different example. In this case, the velocity is not constant. There is an acceleration. So acceleration is the time rate of change of velocity. So it's related to velocity just like velocity is related to position. So the slope of the position graph now changes. So in this case, our truck starts at rest, but its speed gradually increases as time goes by, and the slope of the position versus time graph gradually gets steeper. Okay, so those are the two different types of graphs you'll see. Nice straight line graph if the velocity is constant, and a curving graph, in fact, is parabolic if the acceleration, the rate of change of velocity, is constant. Let's look at the velocity versus time graphs for those same examples. Okay, so here we have again the constant velocity case, and if the velocity is constant, it's a very easy graph. It's in fact just a horizontal straight line, and the area under the curve is the displacement. So let's calculate that. We went 3 meters per second in 10 seconds, so the area is 3 times 10, 30 meters. Positive 30 meters, because we're again saying positive is to the right. Let's do the other case. In this case, the acceleration is constant. So the truck starts at rest, no velocity, and its velocity increases at a steady rate. So the velocity has a constant slope. This gives you a triangle. And so a triangle is pretty easy to find the area of. It's 1/2 the base times the height. So let's see. We ended up going a final velocity of 5 meters per second. 10 seconds was the total time. So we do 1/2 the height, 5 meters per second, the base, 10 seconds, end up with 25 meter displacement. Okay, so that's our introduction to speed and velocity.